So last section for us is on normal distribution. So a normal distribution it's symmetric. It has this bell shape. Like when people refer to the bell curve, this is what they're talking about. It only has a single peak, and that peak is the mean, median, and mode all together. So that top point in the middle is the most frequent value on whatever continuum of numbers we're looking at. It's the middle value, and it's also the average value. So when we have that, then we are going to get this symmetric with a peak. So to define how the rest of the curve goes, we use the standard deviation as the variation. So a small standard deviation means that it's going to drop very quickly. A bigger variation means it will be a wider distribution. Now, some of the weird graphs we looked at in the past that had like a left skew or a right skew were because the mean, median, and mode were not equal. So this does beg the question though, well, how do you know if something's normal? Because not everything we look at is normal. Like quite a number of them are stacked on one side or the other side, and they don't average out in the middle. Or they might be bimodal, like especially if you have men and women within a data set, then for some things like height or weight, you'll see a cluster for the men and a cluster for the women. So it makes two peaks. So here's the conditions. A data set that satisfies the following 4 criteria is likely to have a nearly normal distribution. So first, likely. It's not guaranteed. But statistics is all about likely and probably. So most data values are clustered near the mean, giving the distribution a well-defined single peak. So the bulk of them are like right in the middle. They're spread evenly around the mean. So the mean is not one-sided or the other, it's in the middle and the tails taper off on both sides. Larger deviations from the mean become increasingly rare, so it tapers down. And individual data values result from a combination of many different factors, such as genetic and environmental factors. So genetic are like body measurements, like things, the doctor will measure like average people's blood pressure, or cholesterol probably isn't, strangely, although here's the other thing about normal distributions. If you take a big enough sample, it'll become normal. But in statistics terms, big enough is like, I don't even remember anymore. I think it's over 10% or 20% or several thousand, several thousand a lot of times. But if you get a large enough data set, then you can make the assumption that it's normal. And then when it is normal, we get some lovely effects from it. So this is the probability distribution. We haven't talked about this too much. Let me type this part actually. No, maps the frequency. So a continuum means I can get any of the decimals in between. I don't have singular discrete values. Sometimes we can kind of make an assumption that something is kind of like a continuum. Like if we're looking at test scores, you usually don't see like 97.5 unless I'm grading a test. But you theoretically could get it And if you did, it would be ranked between 97 and 98. So that's some of the other more subtle factors. So the other thing about a probability distribution is the area under the curve, the total area under the curve has to be 1. And if I pick a value, the area to the left of that, so left on, will be the probability of that value in a normal curve. And we're going to do more of this. I'm just trying to set it up. And we actually, it's not that particular value, it's the probability of anything less than that value. So if we look at like those probabilities as we go along the continuum, that also shapes this curve or is shaped by the curve, just depending on your perspective. So here's the thing with normal. Once we have the mean and the standard deviation, I can take those and I can map any normal curve onto that picture, where from one standard deviation down from the mean and one standard deviation up from the mean, because remember, these are numbers on a continuum. So the mean is the middle value and the standard deviation is going to be how many away, and then how many away, and how many away. So between the first two, we get about 68% of all the data values. So we could even cut that in half, and it's going to be 34 from the left first, the lower standard deviation to the mean, and 34% from the mean to the positive standard deviation. Now, if I expand that to 2 standard deviations, now I have 95% in there. So for a normal distribution, 95% of numbers, or a lot of times people essentially, fall within 2 standard deviations of the mean. So if I can assume something is normal, and I get enough data that I can reasonably estimate the mean and the standard deviation, then I can also estimate most people are going to fall between these 2 values. Now, if we expand it to 3 standard deviations, we start getting into teeny tiny stuff. So within 3 standard deviations is 99.7% of all the values, or all the people's measure of something. And there are some things in the past that we thought were normal and now we're not so sure. Or maybe they are, but the tool we use to measure them isn't as accurate as we thought. IQ. All right. So down here we have the more precisely 68, 95, and 99.7 is fine. So we're going to use this to actually estimate the some probabilities for certain curves, like for normal curves, but where we're told the mean and standard deviation. We can use that in conjunction with this idea. Like, check it out here. So SAT scores have a normal distribution. They forcibly have a normal distribution. So the most frequent scoring, which it ends up being a scoring in the middle, is numbered 500. And then 100 gives us the standard deviations away. So 34% will be from 400 to 500, 34% will be from 500 to 600. And that 500 to 600 we know have scored better than the 400 to 500. So like we can measure each of these little sections and they're ranked. So I can definitely say the people on the right side of the curve got higher scores than the people on the left side of the curve. Higher does not necessarily mean better. Because if it's blood pressure we're talking about, you don't want to be on the high end. You don't want to be on the super low end either, but it's better to be a little low than a little high. The SAT actually grades things a little weirdly, or they try to craft it so that the results would be a normal distribution, but it tends to get skewed. So generally not the best example, but it gets the idea across, hopefully. All right, I'm going to pause it there and then we'll come back and do some examples.